Okay, so this is question number 3 of the nuclear physics homework booklet, and in question number 3 we're told that the first artificially produced isotope, phosphorus, was formed by bombarding an aluminium isotope with an alpha particle. Basically, they took phosphorus, they bombarded it, or basically almost like threw alpha particles at this aluminium isotope in order to make phosphorus. So first of all, in part A, we're simply asked to complete the nuclear equation and identify the missing particle. So there were some dotted lines here, so this is where the missing particle goes. They gave us the aluminium numbers, an alpha particle symbol, and all of the numbers for this phosphorus nucleus. We need to work out what this particle was. Now, the very first thing we would need to do is add on the 4 and the 2 from the alpha particle, because as soon as we know those, it makes working out these numbers really easy. So then on this side, we've got a total of 31 protons and neutrons altogether, which means we must have on this side, so we've got 30 here, so we've got 1 left over, which is the 1 there. On the bottom, 13 and 2 make 15. We've already got 15 on this side, so that's a 0. So we've got a particle with a mass of 1 but 0 charge, which is basically a neutron, and that's written as a small n like that. So identifying that particle like that gives you 1 mark. Now in part B, we're told that if this reaction is going to take place, the alpha particle's got to come within a certain distance from the centre of the aluminium nucleus. And we're asked to calculate this distance. And then we're told some numbers. So we're told that the alpha particle is given an initial kinetic energy of 2.18 times 10 to the minus 12 joules. So this is the kinetic energy of the alpha particle when it's a long, long way away from this nucleus, this aluminium nucleus. We're then told, and it's very nice of them to tell us, that the electrostatic potential energy, if we've got 2 point charges, is equal to this thing here. So it's equal to the charge of the first particle multiplied by the charge of the second particle divided by all of this, where r is the separation of the charges. So this is basically the work done by the field to stop this particle as it comes in, because what's going to happen is the alpha particle is going to have kinetic energy a long way away. As it moves towards the nucleus is essentially going to repel the alpha particle, so the alpha particle is going to slow down. So the kinetic energy is going to decrease. But obviously we have to conserve energy, so as the kinetic energy decreases, the potential energy between these two particles increases. Eventually what's going to happen is the alpha particle is going to get so close to the aluminium nucleus that it's going to stop. At that point, that's the point at which it's the separation is as close as it possibly can be. The kinetic energy has gone down to 0, so the potential energy is the maximum. So what we're really saying is that all of the kinetic energy the alpha particle had is transferred to potential energy when they're as close together as they possibly can be. In other words, this equation here, and I've substituted the k for the 1 over 4 pi epsilon naught, just because it makes it easier in the calculations. So this potential energy is equal to this kinetic energy. And so I can just rearrange this equation to get r, and it's r that I really want. So r is equal to the constant, which is the 9 times 10 to the 9, multiplied by the charge of the nucleus, multiplied by the charge of the alpha particle, divided by the kinetic energy. And if I put all of my numbers in here, I get 2.75 times 10 to the minus 15 meters. So that's the d. That's the d that we were asked to calculate. So that was question number 3 of the nuclear physics homework booklet.